Okay, so we are now live both on YouTube and Facebook, and we have some participants here in Zoom as well. First of all, I want to thank everyone that is watching us today. This will be the first session of a series of online sessions that IAPS has prepared for the physics student community, particularly IAPS members, but also anyone who is interested in the various physics topics that we will be addressing. And we will start with a chilly note with the physics of the cryosphere, and to carry us through this voyage of the cryosphere, we have Dr. Richard Essery from the International Association of Cryospheric Sciences, IACS. Welcome, Dr. Essery, and thank you very much for participating in this session. So I will just give you a short bio of Dr. Essery. He has a degree in mathematical physics from the University of Edinburgh and a PhD in polymer physics from the University of Cambridge. After graduation, he joined the UK Met Office to work on the representation of snow in climate modeling, and subsequently held research positions at the University of Saskatchewan and the University of Aberystwyth. I hope I'm reading this correctly. He is currently a professor of cryosphere atmosphere interactions in the School of Geosciences of the University of Edinburgh, and Secretary General of the International Association of Cryospheric Sciences, which he is representing today. So I will now give the word to Dr. Essery to do an initial presentation on the topic that brings us here today, and also on IACS. So I now give you the word, Dr. Essery.
Okay, first thing I think is I don't have permission to share my screen yet. Are you able to enable that?
Okay, you should have it now.
Ah, yes, very good. So can you just confirm that you can see this slide of a glass here now?
Not yet.
Not yet.
Okay.
Does it appear now?
I think now it is streaming the slide.
Okay, so I can begin then. Thank you for the introduction. I am going to be talking about the physics of the cryosphere, but also work of the International Association of Cryospheric Sciences. So I'm going to be starting with some science administration, but please do bear with me because I will get to the physics. And the tools of physics are very widely used, both to understand the processes operating in the cryosphere and to measure those processes. So I can promise you some thermodynamics, some continuum mechanics, and there'll be a lot of electromagnetic radiation. But starting with the administration, the top, at the level of the International Science Council. And the ISC operates on UN level to promote the value of science for evidence-based decision-making on issues of public concern. And feeding into that, there are 40 international science unions and associations. International Union of Pure and Applied Physics, with which IAPS is affiliated, is one of them, and the International Union of Geophysics and Geodesy is another one. Coming down another level, under IUGG, there are 8 associations, one of which is the International Association of Cryospheric Sciences, and that is divided into a number of divisions that are concerned with different aspects of the cryosphere, and there are standing groups and joint commissions that work on issues at the interfaces between those associations. IUGG was founded in 1919 with the aim to rebuild international collaboration in geoscience after the war. The International Association of Cryospheric Sciences only became an association of IUGG in 2007. It's the newest of the 8 associations in IUGG. And I will come back to the history and the motivation for the formation of our association a little bit later. But our aim is to encourage research and collaboration in cryospheric sciences. And to achieve that, a lot of our activity, the work that we do, is involved in organising and supporting conferences and workshops for cryospheric scientists. But we also aim to spread awareness of cryospheric science beyond cryospheric scientists. So thank you for this great opportunity to talk to physicists. There's a lot of behind the scenes work that goes on as well on standardizing and archiving cryospheric data and measurements. So you'll know that linguists argue about what it means to say that Inuit languages have 50 words for snow, but I can tell you for sure that we have a 90-page document classifying different structures of snow on the ground and how they should be described scientifically. And finally, we now have a very important requirement to promote equality, diversity, and inclusion in the cryospheric sciences, recognizing that these associations, for very much of their history, have really looked rather like old boy networks. Just to be clear, the cryosphere is the frozen water on and below the Earth's surface. That is many different things in many different places: snow, glaciers, ice on sea, lakes and rivers, ice sheets, ice caps, ice shelves, and permafrost. And there are many reasons to be interested in the cryosphere and to be concerned for the cryosphere. Snow and sea ice are habitats for many organisms that are adapted to cold environments, and they are endangered by warming. Melting snow and ice provides water for drinking, air power in many parts of the world. Seasonal snow and ice is a natural reservoir that stores precipitation over the winter and releases it later in the year when demand is higher. We also get water from glaciers that are melting, but that is a non-renewable water resource, parts of the world where glaciers are retreating. Trafficability, that word there means the ability to traverse terrain. And if you think of somewhere like the tundra in the north, that landscape is very much easier to travel across, both for people and for animals, when it's frozen, rather than when it is wet and muddy in the summer. Snow is also very slippery, and there is a multi-billion-dollar recreational industry that is built on the slipperiness of snow. On the risk side, when land ice melts, it contributes to rising sea level. Avalanches are very dangerous, both people and infrastructure. Rapidly melting snow can lead to flooding, particularly when rain falls on snow. And when rain falls on frozen ground, it can cause structures to be sheathed in ice, in ice storms, which causes a lot of infrastructure damage. GLOF, that acronym I put there, that is a glacier outburst flood. These happen when glaciers are retreating. They leave behind a terminal moraine that can act as a dam for a lake that forms from the meltwaters, but they're rather unstable dams, and they can break suddenly, releasing very large floods. And Jokelaus, if there are any Icelanders who are listening, will have to excuse my pronunciation, but Jokelaus is a flood resulting from melting of a glacier through geothermal heating, possibly because of volcanic eruptions underneath ice sheets. Permafrost is permanently frozen ground, and when it melts, any structures like this building will subside. So that's, again, a hazard for infrastructure in the colder countries. And permafrost soils also contain a lot of carbon that, when the permafrost is melting, is released to the atmosphere as methane, which is a powerful greenhouse gas. With so many interests in aspects of the cryosphere, there are a lot of other international organizations beyond IACS that are concerned with the cryosphere. Some of them are regional in focus, so there is the International Arctic Science Committee and the Science Committee on Antarctic Research. Some of them are concerned with particular components of the cryosphere, like the International Permafrost Association, the International Glaciological Society, and some are concerned with supporting researchers, these networks for permafrost researchers and polar researchers at the early stages of their career. Returning to IACS and IUGG, within the Association of Cryospheric Sciences, we have 6 divisions that cover different aspects of the cryosphere. And this is not just restricted to the cryosphere on Earth. Ice is the major constituent of many moons and planetary rings in the solar system. And it's not just water ice as well. There's other volatile substances like carbon dioxide ice on Mars. So IACS has a division that deals with research in those areas. And IACS collaborates with all of the other associations in the IUGG. Interactions with atmospheric and oceanic sciences are obviously very important. And our next big conference would have been joint with those associations in Korea next year. But that has had to be cancelled under the current circumstances. And we're replacing it with an online seminar series, rather like you've done with ICPS. So I'll be very grateful that, therefore, to hear about your experience that you can share of running an international online event like this. One particularly important relationship for cryospheric sciences is with the Association of Hydrological Sciences, which was founded in 1922 and established a commission on glaciology in 1927. So cryospheric sciences as an association originally came out of the hydrological sciences. The hydrological motivation for that is that there's the enormous importance of snow and ice melt for water resources. But there's also strong interest in ice as a solid material, regardless of it being frozen water. So IACS was formed to represent cryospheric sciences, but IAS, the Hydrological Society, retains an international commission on snow and ice hydrology. Dividing the physical processes on Earth into different spheres like this in these associations could be regarded as a systems science view of the world. So the Earth system, consisting of separate thermodynamic systems, which would be characterized by thermodynamic state variables, and they interact with their surroundings by exchanges of mass and energy across their boundaries. So you'll find many diagrams like this on educational sites that divide the Earth system into spheres. The atmosphere is the gaseous part, the biosphere is the living part, lithosphere is the solid Earth, hydrosphere is all liquid water in the oceans, rivers and lakes and groundwater, and cryosphere, as I said, is all the frozen parts. As always with systems science, you can choose where you draw the boundaries between systems. You might regard us, as in this diagram, as a system, as an anthroposphere that interacts with the other spheres. But because it is very difficult to reduce human behavior to the level of physics, it's more common to regard human activities as an external factor forcing the Earth system by altering the composition of the atmosphere and the characteristics of the land surface. For the cryosphere, however, a lot of progress has been made by using the methods of physics to understand processes. The cryosphere is very extensive around the world, obviously dominating the polar regions, but all the way to the tropics, there are high mountains in the tropics that can support glaciers, although maybe for not much longer. So I'll look at some of these components of the cryosphere and their global extent. Seasonal snow and sea ice are very dynamic features of the northern hemisphere. I hope you can see that there's an animation running here of looking down on the northern hemisphere of, through the course of the year, the growth and retreat of seasonal snow and sea ice cover. Snow covers about 50 million square kilometers in the northern hemisphere, the maximum each winter. That's about half the total land area, and then shrinks back in summer to pretty much just be covering some high mountains and the Greenland ice sheet. So that's down to about 2 million square kilometers. We can combine satellite measurements with land-based observations back to the 1920s to see that snow cover in spring has declined over recent decades, particularly since about the 1980s. There's also some sea ice year-round in the Arctic Ocean, which expands and contracts through the course of the year. But that has also declined rapidly in recent decades. We can't go as far back with records here. The ground measurements on land are possible because the Northern Hemisphere has a reasonably high population density. Over the Arctic Ocean, in the winter, a lot of the area where the sea ice is inaccessible. So we have to rely on satellite observations, which means we can't go back as far, back to about 1979. And that again shows a strong reduction in the summer sea ice extent of the Arctic Ocean. The question is, to know how much sea ice there is in the winter, how can you tell when it is in a polar night? So how can a satellite see how much sea ice there is? And the answer, of course, is to use physics. And the particular physics in question is the natural thermal emission of microwave radiation from the surface. The microwave emissivity of seawater is much lower than it is for sea ice, so the ice appears much brighter than unfrozen ocean when viewed with microwave radiometer, of which there are several satellite instruments that can make those measurements. Sea ice is floating on water, so it does not cause sea level rise when it melts. The vast majority of ice on Earth is locked up in the Greenland and Antarctic ice sheets, and melting of those would cause sea level rise. Ice is 3,000 meters thick in places on Greenland, and it would take a long time to melt all of that ice, thousands of years. But unprecedented surface melting has been observed on the surface of Greenland in recent summers. There's very much more ice in the Antarctic, which we divide into eastern and western portions. The East Antarctic is mostly very high and cold and will not be melting anytime soon. The West Antarctic ice sheet is of more concern because its base is below sea level, which makes it vulnerable to increasing ocean heat transport melting ice from below rather than air temperature melting the ice from above. There are smaller ice caps around the world, such as those on Iceland, and mountain glaciers as well, much smaller than the ice sheets and will contribute less to sea level rise. But because they are smaller, they're much more sensitive to climate change. Lots of examples of historic and recent pictures that show dramatic change, like these ones, the Athabasca Glacier in Canada between 1919 and 2005. There's a World Glacier Monitoring Service which operates under the association, auspices of the Association of Cryospheric Sciences, and that has recorded substantial mass losses from glaciers around the world over the last 70 years. Permafrost is ground that remains below 0 Celsius throughout the year, and there's a lot of that in the Northern Hemisphere. A quarter of the Northern Hemisphere land is underlain by permafrost, and half of the land is seasonally frozen. This permafrost in the colder areas can be hundreds of meters thick, and the depth of the bottom boundary is determined by geothermal heat from below. Ice doesn't have to be present in the ground for it to be classified as permafrost, but where ice is present, we get some very bizarre landforms that can result. Examples like patterned ground and ice-cored hills, or sorted stone circles. The picture there is on Svalbard, but landforms like this are also observed on Mars. A good place to start with the physics would be the phase diagram of water and the properties of water. So here I've got pressure temperature phase diagram of water and three-dimensional pressure volume temperature diagram. Water, as you know, has very unusual properties due to hydrogen bonding, and these properties are essential for life on Earth. The triple point of water is at a temperature such that liquid water, water vapor, and ice can all exist near the surface of the Earth. And there's two related properties on these phase diagrams that are related and very unusual. The solid liquid line has a negative slope, so the melting point of ice decreases as pressure increases, and the density of water decreases on solidification. So ice is less dense than liquid water about 1,000 kilograms per cubic meter density, ice close to zero, density of 917 kilograms per cubic meter. And that means that water ice floats on top of water and it insulates the water underneath. That keeps lakes in cold regions warm in the winter. If the ice did not float, lakes would freeze from the bottom up and would freeze solid, and life in northern lakes would be impossible. Even before it freezes, water behaves strangely as it cools down. Its density increases as it cools, as would happen with normal materials, but it reaches a maximum at 4 Celsius and then decreases slightly on further cooling. And then the density decreases greatly as the water freezes. That density maximum is only a feature of fresh water. Seawater has about 35 parts per thousand salinity. That increases the density quite a lot, but it also removes the density maximum. So there's no density maximum before seawater freezes, and the freezing point is also depressed. So seawater will freeze at closer to -2 than 0. All this means that lakes and seas freeze in very different ways. But sea ice is not salty. The salt gets squeezed out of the crystal lattice as ice forms. That means that the water below sea ice as it's forming is cold and extra salty, which means that it's extra dense and it's going to sink. And this forms a connection between surface and deep circulations in the ocean. Surface currents are driven by wind. Winds are driven by atmospheric pressure patterns and the Coriolis force. And where the prevailing winds are driving water away from the land, deep ocean water rises up to replace it. This happens to the west of the continents in the tropics. The return of water sinking happens at high latitudes where water is cooling and freezing and becoming more dense as it gets colder and more saline. This is called the thermohaline circulation because it's driven by temperature and salinity. And the circulation transports massive amounts of heat from the tropics towards the poles. This makes the winters much milder in Edinburgh, where I live, than Moscow, for example, which is at the same latitude, about 56 degrees north, but much further from the ocean. And so we get much less snow than Moscow does. Moving on to snow, snow grains form in clouds by the deposition from vapor. And beyond all having basic hexagonal symmetry, there's a lot of diversity in the growth forms of snow crystals, very sensitive dependence on temperature and humidity of the air that they're forming in. And snow grains will experience changes in temperature and humidity as they fall through the air, leading to even more complexity and the common saying that no two snowflakes are alike. But these branched dendritic crystals are very far from thermodynamic equilibrium, and they won't stay like that for very long once they're on the ground. The vapor pressure is higher over the parts of the crystal with greater curvature, so ice sublimates from convexities and redeposits in concavities, which makes the grains become more rounded over time, and it makes larger grains grow at the expense of smaller grains sublimating. And particularly when liquid water is present during melting, there's a rapid rounding and growth of the grains in snow. But weather can interfere with that process. If it's windy, as it often is in ice sheets and tundra areas, the wind can move grains across the surface. They're bouncing along the surface and they are being shattered by the impacts. They're breaking up into smaller fragments, which can be packed together by the wind to make very hard and cohesive slabs of snow on the surface. Strong temperature gradients when the air is very cold lead to vertical vapor transport in snow from the warm sides of grains to the colder sides of the grains because of a vapor gradient again. And that forms large faceted grains that are very poorly bonded together. This vertical vapor transport leads to snow structures that are stronger in compression than they are in shear. So a layer like this can support the formation of an overlying slab, but it will then fail very easily if a crack forms in the slab. And these conditions are very hazardous for avalanche formation. We think of snow as bright and white, but that's not because ice is white. In fact, very pure bubble-free ice is blue, like this blue iceberg. Here I'm comparing ice absorption with the solar spectrum, which is quite close to a black body Planck curve at 6,000 Kelvin above the atmosphere, the red line there. But it's strongly modified by the time it reaches the surface, particularly by ozone absorption of ultraviolet light in the stratosphere and water vapor absorption of near-infrared light in the troposphere. Note that the ice absorption scale here is logarithmic. Ice is very transparent to ultraviolet and visible light, but the absorption increases dramatically in the near-infrared and the red end of the visible spectrum, which is what makes pure ice blue. But snow is not pure ice. It has a lot of grain boundaries between ice and the air. Ultraviolet and visible light can penetrate a fair distance into clean, fresh snow without absorption, and it's scattered at the grain boundaries. There's a very high probability it'll be scattered back out of the snow, so snow has a high reflectivity. You can get a bad sunburn on a sunny day in the snow if you forget that a lot of the ultraviolet light will be reflected back from below, and just wearing a hat isn't going to protect you. But if we could see near-infrared light, snow would not look bright and white because ice absorbs near-infrared light quite strongly. Higher ice absorption means that there's a higher chance that near-infrared light will be absorbed as it passes through snow grains before it's scattered at the grain boundaries. And the chance of absorption increases as the snow grains get larger with age, and the path length between the scattering increases. So the reflectance, the albedo of snow, decreases for near-infrared as the grains get larger. This has very little influence on ultraviolet and visible light, where the absorption is weak. What makes a big difference is if there's something else in the snow that does absorb visible light. And snow, as it sits on the ground, will get progressively dirtier as dust or soot are deposited on it. This picture here is really very dirty snow that is sitting beside a road. As snow ages, it also compacts under its own weight. And if it doesn't melt, it will eventually turn into glacier ice with a density of 917 kilograms per cubic meter at a rate that depends on temperature and the accumulation rate. So as you go deeper inside an ice sheet, the ice is becoming denser towards 900 kilograms per cubic meter. Fresh snow can have densities as low as 50 kilograms per cubic meter and compacts very quickly as the grains round and can compact more closely. 550 kilograms per cubic meter is about as high a density as you can reach by just packing ice spheres randomly. And after that, the compaction slows down because the ice has to deform to become more compacted. Another important transition happens around 830 kilograms per cubic meter, because that's the point at which air bubbles between the ice grains close off and air becomes trapped inside the ice. This is very important use for ice cores because those bubbles inside ice samples from deep in ice shelves and ice sheets are samples of the atmosphere in the past. The air can't be squeezed out by further compaction, and instead it compresses. So if you put ice from a deep ice core into your gin and tonic, it fizzes. Isotopic composition of the ice in the cores also gives proxy information on the temperature when the snow fell. So here are temperature and carbon dioxide reconstruction from a core that was drilled at a site in the Antarctic where the ice is over 3 kilometers thick and the ice at the base is over 800,000 years old. So that covers the last 8 ice ages. When people say that there's more carbon dioxide in the atmosphere now than at any time in the last 800,000 years, this is how they know. Ice cores can give very precise information on the chemical properties of ice, but they're very expensive and time-consuming for deep cores. Information on the physical properties of ice can be obtained over larger areas using radar. Ice is quite transparent to low-frequency microwave radiation, so this is referred to as ice-penetrating radar. The image here was obtained using a multi-channel radar with frequencies ranging from 140 to 230 megahertz. So that's the 1 to 2 meter wavelength range. There's a strong reflection from the bedrock, which shows the thickness of the ice. So you can see here it's around 4,000 meters thick. This is a deep Antarctic ice core. But there are also a lot of reflections from internal layers in the ice. And these reflections are coming from layers of ice with contrasting electromagnetic properties. Near the surface, variations in the density of the snow that was deposited at different times of the year give reflections from variations in the permittivity of the ice. But once the snow is fully compacted into ice, there are no more density variations, but we still see reflections. These come from variations in the electrical conductivity of the ice. And the reason that is varying in some layers is that sometimes the surface has been covered with dust deposited by volcanic eruptions. And I've got another image here from a transect over, so this was an airborne radar flying over 150 or so kilometers. Again, see a strong reflection from the bed, and in the middle of that image, it looks like there's a sharp dip in the elevation of the bedrock, and then a very flat area. That is not bedrock that is very flat for some reason. That is the surface of a lake that is underneath the ice. This is a lake that's underneath 4 kilometers of ice. Many of them, these subglacial lakes, have been found in the Antarctic, but this is the largest of them. It's called Lake Vostok. It's 200 meters deep and 230 kilometers long, and it can exist on the ice, under the ice, because you remember that the melting point of ice decreases with pressure, and this lake is under the enormous pressure of 4 kilometers of ice. Even the bases of much shallower glaciers can be at their pressure melting point, and the pressure of the water helps them to slide. But ice can also flow by deformation. Radar again shows the surface velocity. So this is a shorter centimeter scale wavelength that is scattered by surface features. It's been used to track velocities using interferometry. Over the whole of the Antarctic, this shows ice divides where the flow is very slow. This is usually where ice cores are drilled, and you can also see the location of Lake Vostok marked on there. But around the coasts, the flow is organized into much faster ice streams, where the ice can be moving kilometers per year. You won't be surprised that ice does not flow like a viscous Newtonian fluid, though. Experiments show a stress-strain relationship for ice with an exponent that is around 3. It would be 1 for a Newtonian fluid, and coefficient A that is like an inverse viscosity and depends on temperature. Even these fast ice streams are only flowing at a few kilometers a year. Snow and avalanches can move very much faster than that, particularly if the slab of snow, as it slides, breaks up into powder, becomes suspended and entrains air. Avalanches like this can be moving at 300 kilometers an hour and are very dangerous. You cannot outrun an avalanche like that. I have a video from the Swiss Snow and Avalanche Research Center. I hope this will play over Zoom, of an artificially triggered avalanche. So at the beginning of the video, you'll see a puff of an explosion that was used to trigger the avalanche. So they'd know when the avalanche was going to occur and could film it. So there's the explosion. Slab begins to slide, and those slabs break up into powder, become airborne and suspended. They're breaking off other slabs, but the powder is overtaking the slab. You can see the turbulent entrainment of air and snow in the head of that gravity-driven flow, which is being channeled by the topography. They're moving very fast. One of the reasons that these avalanches are so dangerous is because they're moving so fast and because the snow is airborne, they can run out for a long distance even when they reach the valley bottom, and even can run some distance uphill. So you might be on the opposite side of the valley from this avalanche, up the slope, and think you're safe, but you're not necessarily safe because this avalanche can run up slope as well as downhill. You can see all the turbulence in the head of that gravity-driven flow, and it looks like there's going to be a lot of very interesting physics going on in there. But this is going to be a very difficult and dangerous flow to study up close. I'm just about to wrap up the presentation, and I'm not going to present any conclusions because I really only scratched the surface of the physics of the cryosphere. Instead, I'm going to finish up by talking about an avalanche experiment that I love because it shows really a very physics way of thinking about things. This is a Japanese experiment, and rather than using snow, they used ping pong balls and rolled a lot of ping pong balls down a ski jump landing slope, which is here viewed from the front and in this and side on. And with high-speed photography, they tracked the motion of particles. They measured air pressure as this ping pong ball avalanche flowed past, and they measured the terminal velocity of avalanches with different numbers of ping pong balls. Ping pong ball is very light, and if you roll it down the slope, it's very quickly going to reach a terminal velocity of just a few meters per second, limited by air drag. If you roll a few ping pong balls down the slope, it's going to be very much the same. They'll behave independently. But if you have enough balls, they will begin to behave collectively and will entrain air as they move. And then because the air is moving with the balls, they experience less drag and can fall faster. So these researchers kept adding more and more balls to find how the terminal velocity increases, ending up with 550,000 ping pong balls. As physicists, I bet some of you are thinking, I wonder if the velocity is a power law of the number of balls, but what's the exponent going to be? So we're going to do a common physics trick of trying a dimensionless variable analysis with the variables that the answer could depend on. So, yeah, so if we have a number n balls, they'll have a volume v, which is proportional to the number of balls. We'll have dimensions of meters cubed. They're moving at speed u, meters per second, under gravitational acceleration, which we can adjust for the angle of the slope. And we'll look for a combination of those variables that gives us a dimensionless number. And the one that we can come up with in fluid dynamics would be called a Froude number. If we assume that that number is constant for similar flows, it will give the velocity scaling as the 1/6 power of the number. And that is pretty much what is found experimentally. So I'll end the screen share there and hand back.
Thank you very much, Dr. Essery. I think it was a very interesting presentation, and I think several of the specific topics that you mentioned during the presentation, I will take the opportunity to ask you to elaborate a bit on them. But first of all, I'd like to start by asking you, after this interesting overview of essentially the physics of cryospheric sciences, I want to ask you how your interest in this field arose. Did you consider other fields? Was there a particular point in your journey as a student where you became essentially set on following with studies on the cryosphere?
That came really at beyond my time studying physics. So I studied physics with no really clear idea of which profession that would lead me into, but aware that having training in physics would open up a lot of different opportunities. So doing a PhD in polymer physics, the obvious thing would have been to move into industrial research. And I considered that, but I looked around for other possibilities as well. I thought maybe something more in environmental physics would be more interest. And this was in the early 90s, which was a time at which climate research was expanding very greatly. It was the early days of climate modeling and climate prediction science. So opportunities were arising in that field. So I started my career in the UK Met Office in climate research. And climate modeling, Earth system modeling now takes in a very huge range of physical and biological processes. So we need people with a lot of range of different expertise. And it just happened that the area that they were looking into when I started work at the Met Office was how to represent snow cover in climate models, which is important. One of the important features of snow in the climate system is that very high reflectivity that I mentioned. So snow reflects a lot of sunlight. If the atmosphere warms, snow melts earlier. The land surface is darker without the snow. It absorbs more solar radiation, and that reinforces warming. That's a positive feedback on warming, which is one of the reasons why we're very interested in snow in the climate system. I had worked purely on the theoretical sides of that for a number of years at the Met Office, and I took the opportunity to do a postdoc in Canada that involved field work as well in snow, which was an area I wanted to get some more experience in. And the combination of modeling and field work in snowy environments was very appealing. So that is what really brought me into that field. It was a process over a number of years. So that's quite a long answer to your question.
No, it's great to know that and to essentially show a bit of the different types of, let's say, career paths that await physics students of various fields in their professional futures. And I think it's very interesting that essentially, in fact, you mentioned several points related to that during the presentation as well. So there's a lot of, in terms of research and in terms of studying within the field of physics related to the cryosphere, there's obviously a lot of focus on climate science and on particularly in what essentially the observations that prove that in fact climate change is happening and it is provoked by human activity. And regarding that, I wanted to ask you, what is essentially IACS itself? How is this addressed, not only in terms of research and collecting evidence and proving the phenomenon itself, but how does IACS address this in terms of, let's say, pushing for public policy, which we know, of course, is essential in tackling this issue? So does IACS get involved in any way in maybe pressuring or counseling public decision makers at the international and even at the national level into, doing what is necessary and what is recommended by the scientific community to actually address and prevent that climate change evolves to a point that is essentially unbearable?
The major way in which we can contribute to that is by summarizing the scientific evidence and presenting it in forms that will be accessible to policymakers, politicians, decision makers. The main process for that in climate science is the intergovernmental change, which produces a report on the science of climate change every few years. The next one is in preparation just now, and that goes quite deep into the science, but will always contain executive summaries for people who maybe don't have the scientific interest to follow all of that, or don't have the time to follow all the evidence. It is summarized. The IPCC just last year produced a special report on climate change in the cryosphere and the oceans, and IACS scientists were very, very heavily involved in that.
Very well. We actually, I can already mention in the sense that luckily one of the sessions that we will have will be precisely with representatives of the IPCC to give, because essentially it's important that not only we talk about and we address the issue of climate change, but also that we show just how much like multidisciplinary the research is, and how many different fields sort of converge to show a deeply concerning phenomenon that we need to address very urgently. I will just ask anyone that is watching us. I'm following all of the platforms where we are streaming this session. So if you have any questions that you'd like to ask Dr. Richard Essery, I will read your comments and I will present them during this the session. We are now, we've been for a bit since the end of the presentation in the part of a Q&A in this session, and continuing in that spirit, I want to ask about maybe if you could elaborate a bit further on another topic that you mentioned, in fact another thing that you mentioned, which is essentially that so ice or a cryosphere essentially isn't restricted to the Earth. So there's already observations of ice and cryospheric structures in moons, in exoplanets. And I wanted to ask you if usually how promising do these observations tend to be in terms of the outlook and the consideration of if a planet has in the past or currently has or will be able to develop life in the future because of having essentially a lot of times cryospheric structures that basically ensure that there's water below that might or might not at some point be able to house life, let's say.
Yes, so there are very clearly glacial landforms on Mars. So I mentioned the pattern ground. There are things that look very much like debris-covered glaciers we have on Earth, or on Mars as well. There is a fair amount of ice on the Moon, which will only survive in craters in shadows where the sun never shines, which would rapidly sublimate that ice. In terms of the interest for life in the cryosphere elsewhere in the solar system, the most interesting candidates for that are icy moons like Io that have an icy surface but could have liquid water underneath. This is one of the interests in these subglacial lakes that I mentioned. So Lake Vostok has been sealed by ice for 15 million years. It's under 4 kilometers of ice, so there is no sunlight there. But there is possibility that there is microbial life in it that gets its energy from chemical processes. So Russian scientists have drilled into that lake with the one of the things to look at is if there's any signs of life in that subglacial water, and it is very hard to interpret, and it is hard to separate from the possibility of contamination from the surface in the drilling. But it is believed that there is a microbial ecosystem in Lake Vostok under 4 kilometers of ice that has been cut off from the rest of the world for 15 million years.
Thank you very much for that answer. I think that this is indeed a very interesting aspect in terms of the study of the cryosphere. And in fact, there's still a lot to develop in this sense. I want to bring you a question from one of the students watching us. Which is the rising temperatures on Earth will decrease the extent of the cryosphere. How is that affecting the field of research? As an exaggeration, why should we continue studying or specializing in that field when the matter of interest is melting away?
As I said, so some of this ice is kilometers thick. It will take a very long time for Greenland to melt. But as it does, it will contribute to sea level. So with the reductions in the cryosphere is a lot of the motivation for studying. It's not the only reason to study the cryosphere, but it drives a lot of the research questions and hazards that arise from a declining cryosphere and how to adapt to those. So it will still be around for a long time yet.
Very well. There is another question. Can you tell us more about the physics of how pattern formation occurs in snowflakes?
I can tell you a bit more about this. I can tell you a good resource for this is there's a paper called the Physics of Snowflakes, and it's by Ken Lebrecht. If you have a recording of my presentation, there was a link to that, or there was a reference to it on the slide that was about the growth of snowflakes. The dendritic forms that are really the kind of the classic poster example of a snowflake, are forming by a diffusion limited aggregation process, which you'll see in a lot of other systems that lead to the formation of dendritic structures, that water molecules are being deposited from vapor onto the crystal structure, and it is easier for those water molecules to be deposited on the points of the structure than deep into the structure where they'd have to diffuse further in, which is how those kind of dendritic structures arise. But they are, as I said, that then makes very non-equilibrium forms when they stop drying. They then become rounded very, very quickly. And if you do go and read that paper, you'll find that a lot of the physics of snow crystal growth are still not well understood.
Very well, thank you very much. We currently don't have any other questions from the audience, so I will ask you if your work has been essentially theoretical, but I wanted to ask you if you could give a sort of outlook of the involvement that there can be in terms of more experimental work, and also in terms of engineering, for example. Speaking at least for my country, in Portugal, a lot of the growth in terms of study in physics has been precisely in the area of physical engineering. So I think it is also important to try to give this idea of the kinds of involvements that there can be in those senses.
Okay, yes. So my work has mostly been involved theoretical and modeling. But I have been lucky in being able to combine that with field measurements, which is very good discipline for a modeler to be exposed to the processes that you're studying theoretically, to study them experimentally in the field. There is laboratory work that is relevant as well. So I mentioned that there are still open questions about pattern formation and the growth of snowflakes. It would be very difficult to study those processes in a cloud. So some people grow snowflakes under very controlled laboratory conditions. We can give a lot more insight in that way. Engineering, a particular application there is that a lot of the information we get from on the cryosphere is from remote sensing, from satellites, and radar is very important in that, for its ability to penetrate through clouds to see the surface, to penetrate through the surface to see subsurface structures. So there's a lot of satellite and radar engineering that is still very important to do. In my particular interest in snow measurements, the particular wavelengths of radar that we think would be particularly useful for measuring snow properties are currently not available on any satellite sensors. So there's a lot of engineering applications that would be interest to us.
Okay, thank you very much. I would ask you an additional question. So in terms of your involvement in IACS particularly, can you maybe elaborate a bit about how you became involved and how that involvement with an organization like IACS usually happens? Is there Is it sought out by a big majority of the field? So if you could elaborate a bit on that.
Yeah, so a lot of people in the field will be involved in some way or aware of the work through the work that these associations do in organizing conferences. So the International Union of Geophysics and Geodesy has a big international conference every 4 years. And right when I started out in my career, I went to one of those conferences. This is very good experience at the early career stage, being at one of these big international conferences where you meet a lot of people and see different fields as well and how they interact. So I was attending those conferences. Another thing that we do is we have working groups that will run for a period of 4 years and address a particular issue. And a little bit later on in my career, I had an idea for a piece of research that would work. Proposed that to the Cryospheric Society when it was still within hydrology. So I was chairing one of these working groups, which meant I would be invited to the committee meetings with the association to report. So I get to know a little bit more about the administration of these societies, and then eventually we have quite a high turnover in the membership of these committees to keep refreshing things. So eventually, just by being present at conferences and knowing a lot of people involved in the field, they asked me if I would be willing to be the Secretary General of this association for a period. I'm doing that at a fairly advanced stage in my career, but a lot of the people who we have involved are at earlier career stages, and we're keen to have the involvement of people at early career stages.
Very well. Thank you for that answer as well. And I think we are potentially approaching the end of this session. I'll keep following. I have another question for you, but I'll keep following all of the platforms where we are streaming and see if any more questions come up as you reply to my question. So I wanted to get an idea of just a general thought of the expectations that there is within the field of studies of the cryosphere, and particularly in your view and in terms of your research, what kind of expectations you have in terms of the development of research within your own studies, and also, for example, in fields such as climate change, which we have already addressed a lot, but also in other topics that you that might pop up on your mind as you give us this general expectation.
Yes, we have some areas of climate science where the physics is not well understood, and there's requirements for more fundamental research. There are other areas in which the physics is very well understood, but the challenge is to apply that physics on very large global scales and on long time scales of climate change. And opportunities are arising with increasing computer power to include more of the physics and more processes into climate models. So particularly in the cryospheric area, there is a lot more ability to include physics of ice sheets and sea ice that is well understood, but requires very high computational effort. Another emerging area is with improving satellite technology and longer records, we now have very large data volumes to deal with, and there's quite an expansion in machine learning methods now. That's something that we're often seeing people coming into PhD studies now with strong areas in interest in that area, and a lot more expertise than those of us who've been working in the field for longer with lower computational resources.
Okay, thank you very much. I actually thought of another thing that I wanted, a follow-up question that I wanted to ask you before this one, which is how, so in terms of the field of the cryospheric sciences itself, how is it sort of spread out across the world in terms of involvement of physicists in this field? Is there, does IACS in a sense engage in sort of outreach in promoting the field and trying to get sort of the interests of students and professionals from a bit around the world?
Yes, now this is an important consideration. A lot of the support for research in the cryosphere is in the richer countries, and we would like to spread that expertise more. So one of the things that IACS does with the workshops and conferences that we support is also support participation in those. So we don't have a very large budget, but we use that budget to support participation, particularly from early career researchers and from countries that have less of a history of cryospheric research. Another big consideration for cryospheric research in the Arctic is that all the countries that have territory in the Arctic are developed, rich countries, but there are considerable deprivation actually in the Arctic in those rich countries, and less engagement of local populations in scientific research that is done in their regions. So that is something that we're also keen to widen the participation and engagement.
Very well. I think those are very interesting and important efforts. So I was checking here if there were any further questions from the viewers, and it seems that there aren't. And I think we have sort of gone through a lot of extremely important points, not only on the topic itself of the physics of the cryosphere, but also on some particularly the dynamics of the community of physicists working on this topic and involved in IACS in particular. So now I want to ask you if there is any sort of closing statement that you would like, or message that you'd like to leave, particularly the students watching us.
I would say congratulate you on the the choice of studying physics, which I've found very inspiring and can lead you in many different directions. So do take an interest in other fields that could maybe really make use of people with the skills that a physics training gives you. And other than that, just thank you for this invitation and opportunity to be talking with you.
Okay, thank you very much for being present, Dr. Essery. This has been a great time, and I think it was a very good start of this IAPS at a distance calendar of activities. Unfortunately, this year we didn't get to have our main events where especially Planck's and the International Conference of Physics students, where we usually have several hundred students from dozens of countries sharing their love of physics. But we hope that this sort of fills that void in a sense. And I think this was definitely a great start to this calendar. I want to thank everyone that has watched us and keep following IAPS on social media. We have another session tomorrow about LGBTQ+ people in physics. So we hope you participate in that as well, and that you watch the calendar, the further sessions that we will have throughout August and early September. Thank you very much.
Thank you.